Hey students, in this video we're going to cover applications of exponential and logarithmic functions. So we're going to solve compound interest problems, exponential and growth and decay problems, and use logarithms to determine the strength of passwords. So first, compound interest. So if you invest an amount A into an account that has an interest of I, and we have an annual rate of R, and we have an investment of P, and after T years, it compounds N times annually, we're just using this formula: A equals P times 1 plus R divided by N to the NT power. Again, R is the annual interest rate. I should say this is as a decimal, just so we're not confused, as a decimal. And N is the number of compoundings annually. So like that could be 12 if you were doing monthly, 52 if you were doing weekly, and 365 or so if you were doing daily. And P is the principal amount invested, and T is the time in years. So for this first example, suppose $2,000 is invested in an account which offers 7.5% compounded monthly. We want to write a function that models that scenario. So for A, so we're substituting this into A equals P times 1 plus R divided by N to the NT power. So in this case, we're looking for the amount after investment. So for part A, we're going to get A equals 2,000 times 1 plus 7.5% as a decimal is 0.075 divided by N. N is the number of compoundings. In this case, we're compounding monthly. So that's going to mean N equals 12. So 0.75 divided by 12 to the, again, N is 12. So 12 T power. And if we want to simplify that, we can simplify what's in parentheses, this 1 plus 0.75 divided by 12. So let's see what that is. So 1 plus 0.075 divided by 12. So 1.00625. So this is 2,000 times 1.00. How many zeros was it? 2 or 3? 2. So 1.00625 to the 12T power. That's our model. And so then how much is in the account after 5 years? That is just us substituting 5 in for T. And so we can say for part B, we're going to get A of 5 is going to equal 2,000 times 1.00625 to the 12 times 5 power, which is just 60. So let's see. So we're going to get 2,000 times 1.00625 to the 12 times 5 power. So 12 times 5. And that is 2,906.59. So 2906.59. So 2906.59. So for part C, how long will it take for the investment to double? So that means that we want $4,000. So how long will it take for the amount after investment to be 4,000? Well, we already have our model. So for part C, we're solving the equation 4,000 equals 2,000 times 1.00625 to the 12T power. And this is a case of an exponential function. Oh, give me my eraser back. Come back, eraser. Tap again. All right. So this is a case of an exponential function. Let me get some room here. So all right, let's take some of this out. All right. So we want, we can write this up here so we have more room. So 4,000 equals 2,000 times 1.00625 to the 12t power. Again, I need that eraser. Get that out of here now. All right. So remember, solving an exponential equation, we want to first isolate the exponential. So we're going to divide both sides by 2,000. So we're going to get 2 equals 1.00625 to the 12t power. And then because we can't express that 1.00625 as a power to get 2, we put a logarithm on both sides. So the ln of 2 is equal to 12t times the ln of 1.00625. And from here, since we're trying to solve for t, we're just going to divide by 12 times the ln of 1.00625. So t is going to equal the ln of 2 divided by 12 times the ln of 1.00625. And let's see what that turns out to be. So we're going to get the ln of 2 divided by, then in parentheses, 12 times the ln of 1.00625. And it seems like that's 9.27. So t is going to equal 9.27 years. All right, and so you can go back and check that in that compound interest formula to see if that gives you something close to 4,000. The next thing is continuous compounding. It's just like the compound interest formula, except instead of the 1 plus r divided by n, we're just using Euler's number. So the e, it replaces the 1 plus r divided by n part. And so all we need to know is the rate, the interest rate as a decimal, and the amount of time in the principal. So then, for example 2, we're going to take the same values that we had from example 1. The principal is 2,000. The interest rate is 7.5%. We want to write a model for this scenario doing continuous compounding. So for A, we're going to get the amount after investment is going to be 2,000 times e to the 0.075 t power. And then we want to know how long until this amount doubles. Well, it's the same equation. So we want to know when the amount is 4,000. So we're going to get 4,000 equals 2,000 e to the negative 0. Not negative. I don't know why I put a negative. Ignore that. It's just 0.075 t. And again, because it's an exponential, we want to isolate the e. So we're going to get 2 equals e to the 0.075 t power. Since we can't express e as a power to get 2, as an integer power to get 2, we're going to put an ln on both sides. So we're going to get the ln of 2 equals the ln of e to the 0.075 t power. Remember, Euler's number has the property that the ln of e to anything is going to be that anything. So we get the ln of 2 is 0.075 t. And so the ln of 2 divided by 0.075 is equal to t. And so let's see what that is. So the ln of 2 divided by 0.075 is 9.24. And so 9.24 equals t, which was really close to that value that we got in example 1, which means that there is not much difference between compounding continuously versus compounding using a fixed number of compoundings in a year. Example 3, the law of uninhibited growth. If a population is going to increase without bound, and we have like n number of an organism, then we're going to have this formula n of t is equal to n sub 0 times e to the kt. Now notice that looks just like the a equals p times e to the rt. The only thing that we changed is we made the n sub 0 a p, and instead of r, we're using k. So there is the same formula as the continuous compounding. In this example, we have a strain of E. coli has been determined to double every 20 minutes. And we know that at the initial time we have at t equals 0, we have 1,000 bacteria. For A, we need to find the growth constant rounded to 4 decimal places. For B, we need to write a function that models this, and we need to know after that how long will it be until we have 9,000 bacteria. So the key parts here are that we have a doubling time of 20 minutes. So using this model, n of t equals n sub 0 times e to the kt. So the doubling time is 20 minutes. Now, t can be anything. In this case, any units. So t is going to be in minutes for this example. So we know that after 20 minutes, we should have 4,000 of those E. coli bacteria. So 4,000 is going to equal 2,000, because that's n sub 0, e to the k. And again, t was 20 for this. So we're going to divide both sides by 2,000. So we're going to get 2 equals e to the 20k power. We're going to put a logarithm. So this is all for part A, by the way. So then we're going to get the ln of 2 equals the ln of e to the 20k, which remember, that's just going to be 20k. So we don't need that middle part. So the ln of 2 divided by 20 is equal to k. So that's for part A. So the ln of 2 divided by 20 is 0.0347. So 0.0347 is equal to k. Then for part B, we have to write a model for this. We're going to have the number of bacteria after time t is going to equal 2,000 e to the 0.0347 t power. And for part C, we want to know how long it's going to take for the bacteria to get up to 9,000. So if it doubles every 20 minutes, after 40 minutes, we should have 8,000 bacteria. So we expect an answer greater than 40. So for C, we're solving the equation. When does, so 9,000 equals 2,000 e to the negative, why do I keep doing negative? 0.034747 t. And we're going to divide both sides by 2,000. So we would get 4.5 equals e to the 0.0347. All right, I can't write today. I don't know what's going on. Take that back. Give me that back. All right, so why is this? All right, so e to the 0.0347 t power. And again, we're going to put a logarithm. So the ln of 4.5 And the ln of e to that exponent is just going to be the exponent, so 0.0347t, and then the ln of 4.5 divided by 0.0347 is equal to t. See what that is. And again, our answer is going to be in terms of minutes. So it was the ln of 4.5 divided by 0.0347. Oh, I forgot the division symbol. Divided by 0.0347. So like 43.35 minutes. So 43.35 minutes is equal to t. And again, that makes sense because the doubling time is 20 minutes. So to double from 2,000 to 4,000 would take 20 minutes. To double from 4,000 to 8,000 would take 40 minutes. So somewhere after that should be where we hit 9,000, and shortly after that. For example, so next we have radioactive decay, which is the same formula, except K is going to be negative. And so radioactive decay is used for half-lives of elements or radioactive elements. And we're using this formula A of t equals A sub 0 times e to the kt. And again, that's the same as this nt equals n sub 0 e to the kt. Instead of a's, we have n's, and that's all that's different. So for example, 4, we have this cobalt 60 has a half-life of 5.27 years. And in a sample, there are initially 50 grams present, and we need to find the constant of decay. So what a half-life means is that's how long it takes for that substance to divide in half. So if we start with 50 grams of cobalt 60, after 5.27 years, we're going to have 25 grams. And after 10.54 years, we're going to have 12.5 grams and so forth. So for A, we need to find the constant of decay. So remember, we're basing this on A is equal to A sub 0 e to the kt power. And so knowing the half-life is helpful. So after 5.27 years, we should have half of that 50. So that means that when the amount is 25, that's going to equal 50 e to the k times 5.27. 5.27. Because after 5.27 years, we get half of that. So then we divide both sides by 50. So we're going to get a half. I'm just going to write 0.5. So 0.5 is going to equal e to the 5.27 k power. We're going to do an ln on both sides. So the ln of a half is equal to the ln of e to the 5.27 k. So that's going to be 5.27 k equals the ln of 0.5. And the ln of a half divided by 5.27 is equal to k. So in a calculator, let's see what we get. What was it? The ln of a half. So the ln of 0.5 divided by 5.27 is negative. Man, why do I keep forgetting the division symbol? Divided by 5.27. So negative 0.1315. So that is negative 0.1315. And again, for decay, that should be a negative value. So for B, we're just going to write our model right beside this. We're going to have A equals, so the initial amount is 50. So 50 e to the negative 0.1315 t power. And for C, we want to determine how long it will take for 90% of the material to decay. So if 90% decays, that means we have 10% remaining. So that just means we want to know when A is 10% of 50, which is 5. So for C, so for part C, we're solving the equation 5 equals 50 e to the negative 0.1315 t power. And we're going to divide both sides by 50 and give us 1/10. So 1/10 equals e to the negative 0.1315 to the t power. We do a logarithm on both sides, so we get the ln of 1/10 equals negative 0.1315 t. And so the ln of 1/10 divided by negative 0.1315 is equal to t. So negative 0.1315. All right, so we had the ln of 1/10, and that's divided by negative 0.1315. So 17.51 years. That's going to be 17.51 years is equal to t. All right, and so for our last example, it is password strength. So, and this is something we can all relate to when you get that password is extremely strong or is extremely weak or something when you're creating a new password. There's a way to measure this. If you go into computer science, you'll learn a lot about this log-base 2 thing. So H is called the entropy in bits, which is there are 8 bits in a byte. That's all computer science stuff. Of a randomly generated password that contains L numbers of characters. So that means like a 8-character password, for instance. And N is the possible number of symbols. So that's like the uppercase and lowercase letters and digits and whatever symbols they tell you can include. And in general, the higher value of H is going to mean you have a stronger password. But that formula is H equals L times log base 2N. So if an 8-character case-sensitive password is comprised of letters and numbers only, find the information entropy. So remember, the formula is H equals L times log base 2 of N. L is the number of characters in the password, and N is the number of available symbols. So if we have a case-sensitive password, that's going to mean we have 52 letters, 26 uppercase, 26 lowercase, and numbers from 0 to 9 is going to be 10. So we get 10 available numbers. So in total, we have 62 possible symbols or characters we can use. So for this first part, we're going to have H is equal to the 8 characters that are in the password multiplied by log base 2 of 62. That's it. Let's put that into a calculator. So we have 8 times log, and we wanted it to be 62, and that was base 2. Ignore what I'm doing right now. It's just how you have to put it into this calculator. And that's going to give us an entropy of 47.63. So that equals 47.63 in terms of password strength, which seems pretty secure. So how many possible symbol options per character is required to produce an 8-character password with an information entropy of 60 bits? So that means in this case, H is 60. So we're solving 60 equals 8 times log base 2, and we're looking for N. So we're just going to put in a capital N. So how many letters, numbers, and in this case, likely symbols are going to be needed. So to solve this equation, first we're going to divide by 8. And so we're going to get 60 divided by 8 is whatever it equals. So 60 divided by 8 is equal to log base 2n. What's that? 7.5, I'm pretty sure. So 7.5 is equal to log base 2n. And remember, when you have a logarithm, only one logarithm on one side and a value, you make an exponential equation. So we're going to get 2 to the 7.5 is equal to n. And then let's see what that is. So 2 to the 7.5 power is 181. So we would need 181 available characters to do that. And that's really not going to be possible. So that entropy of 60 is going to be extreme. 50 probably is the high end of that. Anyway, we do get 181, which is not possible given just the English alphabet and number system. Anyway, that concludes our video over applications of logarithms and exponential functions.